Thus we see that because the velocity in one frame is the velocity in another frame minus the difference of the velocities in the two relative frames, it's impossible to have c is equal to a constant without contradicting our basic notions of space and time that are the absolute foundations of Newtonian mechanics. It turns out, as we mentioned last time, that Maxwell's equations are relativistically correct and not Newton's equations. And in this conflict, one had to choose between either Maxwell's theory being wrong, which said the speed of light was the same no matter what you did, no matter what the velocity of the observer, no matter what the velocity of the source, or we had to give up Maxwell's equations. Einstein was correct in, Newtonian equations. Einstein was correct then in his work where he gave up the Newtonian theory. In relativity, length and time will no longer be separately invariant, but rather we will have an invariance like this, which is a very strange type of metric, as we will see. That's exactly the result of a light wave, which must be the same to all observers. And if we think of a light wave, such as from a flash bulb emanating out from a given point, as a flash bulb goes off, say for a camera, the wavefront must be a perfect sphere, and the distance or the radius of that wavefront must be the speed of light times time. Distance is equal to velocity times time. Or c squared t squared minus r squared must be 0. Now you can see why we get that this form must be the same, and it must be the same for the primed frame. In other words, if that flash bulb goes off and it disappears, who's to say where the origin of that frame is? Is it to the observer without the prime or with the prime, who's moving at a relative velocity with respect to them? So this will be our new invariant. We now look at our postulates of relativity. First of all, we postulate that the laws of physics are going to be form invariant among all the frames of reference moving at a constant relative velocity, that is, no acceleration. That means that the form which these equations of physics take, the foundational equations, must look identical no matter which frame of reference we use to frame that law. That's our postulate number one. Our second postulate is that the velocity of light is going to be a constant to all observers and invariant. And the third is one that's usually not stated in most of our books. Namely, there's an assumption that the relationship between the two frames of reference be linear. In other words, the transformation between x, y, z, and t to x prime, y prime, z prime, and t prime must be a linear transformation. Therefore, we must have a linear transformation that preserves the speed of light for all frames of reference and gives us form invariance when we go from one frame to another. Looking now at what this transformation is going to be, it is called the Lorentz transformation. That is because not Einstein, but Lorentz first wrote down this transformation, although his interpretation of the transformation was quite different from that of Einstein. He still gets credit for the transformation itself. Rather than use the variables x, y, z, and t, we're going to change to a new notation. x0, which is c times t, x1, which is x, x2, which is y, and x3, which is z. This gives us the same units for x, y, and z, and also for the time portion, because we're now measuring time in the amount of distance light will travel in that amount of time. So if we look at 1 second, rather than measuring it in 1 second, we would measure it in the distance that light would travel in 1 second, which is 186,000 miles, or 3 times 10 to the 8th meters. The light that we mentioned last time in that wavefront from a flash bulb that flashes when the two origins are coincident must be the same. And we're just going to use, in fact, imagine a coincident sphere, but we only need the x direction for this. So we're not going to use the y and the z direction. And so what we're looking for is an invariance between x0 squared and x1 squared in the bar frame. That's one with where I've drawn a bar over it. That's the moving, quote, the moving frame, and the unbarred frame. It turns out that this type of transformation is maintained by a linear transformation, part of the general linear group, in the following form: that x0 bar and x1 bar are given in terms of x0 and x1 by the linear transformation that consists of the hyperbolic sines and cosines. We write, as most physicists do, that CH psi is really COSH psi, hyperbolic cosine, hyperbolic sine, and the hyperbolic tangent being, as you know, the ratio of the hyperbolic sine to the hyperbolic cosine. This is basically goes back to the trigonometric identities that one has. One recalls that sine squared plus cosine squared is 1, but hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. And that minus sign is exactly what manifests itself here, allowing us to have this invariance. We now specifically prove that that transformation is correct by substituting in the exact form for the transformation, which, as one could see here, would be x0 would be ch psi times x0 plus sh psi times x1, and likewise x1 bar is ch psi times x0 ch psi times x1. If we substitute that into this form here, we must get an identity. That identity is seen in the following, where we actually perform the substitution. There's the first term squared, the second term squared. We can see from the first term squared minus the second term squared that we get xo squared plus x1 squared plus twice the cross product. And here on this term, minus the first squared minus the second squared minus twice the cross product. Now the cross products here vanish, cancel each other, I should say. And here we're left with x0 squared minus x0 squared times this. And this is exactly the format that I just referred to when I said this was the root of the invariance of the form, the difference in the squares of two terms being the hyperbolic cosine and hyperbolic sine. Since this is equal to 1, it means that we get x0 squared, and over here minus x1 squared. So consequently, we have proved now that x0 squared minus x1 squared in the barred frame is equal to x0 squared minus x1 squared in the unbarred frame, and is therefore left invariant. Now, I haven't actually proved that this is the form. I proved that this form works. But one can convince oneself with some work that this is the only form that works. And in fact, one can furthermore show that the hyperbolic cosine of the angle can be written as 1 over 1 minus v squared over c squared, the hyperbolic sine as v over c over the square root, and the hyperbolic tangent is v over c. Consequently, our Lorentz transformation can be put in the form L mu nu, and you'll notice here that for reasons that will become apparent later, we have one upper and one lower index. The lower index is moved slightly to the right of the other one. You always have to write these indices where they, the order of the indices, as well as whether they're upper or lower, matters, is given by this particular form, which is also equal to this particular form here according to these two equations. In more elementary relativistic mechanics classes, one commonly sees this form here with all of the square roots. It's easier to see the beauty and the formalism when we write it in terms of the hyperbolic sine and the cosine. Generalizing now to 3 dimensions, we can see that we really must have an invariant metric, because there's no difference between the x direction, the y direction, or the z direction. So it is this time direction minus the other 3 directions squared that must be our invariant. Therefore, the general invariant metric, g mu nu, with 2 lower indices or 2 upper indices, is defined as, and I probably should write a definition here, this exact form here, where mu and nu are equal to 0, 1, 2, 3, being the time, x, y, and z components. The metric g mu nu and the Lorentz transformation L mu nu are the most important tensors in relativity. As you have probably surmised, x0, x1, x2, and x3 are the four components of an object that is called a vector in what is called a linear vector space. These are the coordinates of a point in a space and have certain types of properties. If we think of these as making up a column here, x0, x1, x2, and x3, we generally say that we can refer to any arbitrary one of these as x mu, where mu is an index that refers to mu is equal to 0, 1, 2, or 3, and therefore referring to CT, x, y, and z. This gives us a point in this four-dimensional linear vector space. X mu is actually called a contravariant vector, and it transforms under the Lorentz transformations to a new vector according to the transformation x bar is equal to L mu nu, x nu, where we use the Einstein summation convention over repeated indices. For example, we write L mu nu, x nu, to automatically mean a summation out here over all values of nu, 0, 1, 2, 3. Explicitly, this means L mu 0, x0 plus L mu 1, x1 plus L mu 2, x2 plus L mu 3, x3. This just keeps us, along with Einstein, from having to write summations again and again in all types of equations, and just keeps our notation simpler. It is very important to keep the notation as clean and as simple as possible, and therefore to let us see the forest for the trees. Any ordered n-tuple of real numbers that transforms exactly like x mu does under this transformation, right here, the Lorentz transformation, is called a contravariant vector. Furthermore, this linear vector space has a metric that we just mentioned, and that metric allows us to take a product between two vectors and form a concept of length using this inner or scalar product. And that inner product is formed in the following way. We take our metric g mu nu, which we've just defined as having the same lower indices, which is 1, plus 1, minus 1, minus 1, minus 1, and it makes the space into a metric space with the product g mu nu, dx mu, dx nu, where these are infinitesimal changes in the coordinates. This is by definition a length called d tau squared. In general, when we add a metric or a scalar or an inner product to a linear vector space, that gives us a concept of length of a vector, and the length of a vector allows us to define both the length and the angle. It allows us to come up with the angle between two vectors in particular, or the length of the distance between one vector and another, that is, the difference between two vectors. It's important to reflect upon this just for a moment, that we have a four-dimensional space-time, x0, x1, x2, x3, and a single point in that space is where an event occurs. An event is like a firecracker. It happens at a time and at an x, y, z coordinate. So this is a space of events. Much like you meet a person for lunch. You meet them at a time, at an x, at a y, at a z coordinate in an entire three-dimensional structure. That vector that points to that event is a contravariant vector, and it has upper indices as indicated by the x mu that are here. Anything that transforms to another observer exactly as that does, given the Lorentz transformation, will be designated as a contravariant vector. It turns out that in physics we want things to have definite transformation properties. They must transform as a scalar, a vector, or as a tensor, or some clear and unambiguous way. Otherwise, something would have different transformation properties to one person and to another person. One of the greatest difficulties in relativity is to understand that time itself now is the component of a vector. It will, as we rotate through x, y, and z, be unchanged, and as we translate through x, y, and z, be unchanged. But under the Lorentz transformation, time and space will mix up with each other in a very complicated way. That means, of course, that time is not a scalar, and it will also lead to us later on in realizing that we cannot take a derivative with respect to time, and we must have a new way to parameterize paths through space-time and to look at dynamics. We have just written an invariant d tau squared, which is dx naught squared minus dx1 squared minus dx2 squared minus dx3 squared. This object is a scalar and means that it is unchanged under all of the Lorentz transformation. We can also see that from the fact that here we have the square of this term minus the square of that term. And this is what we have made invariant and forced to be invariant by the Lorentz transformation itself. So you might say that we kind of defined this metric, 1 minus minus minus. And that metric being defined, we looked for transformations that left that metric invariant, and that defined our allowable transformations. This in particular, infinitesimal vector difference, is also invariant under translations in 4 dimensions. That's because this is an infinitesimal difference in time, and if we move our system forward 4 hours, both the lower and the upper part of the dx naught move forward, so a change in time is not changed at all by translation. The invariants under the Lorentz transformation L mu nu will later define what we call the Lorentz group, and consequently the Lorentz algebra, or the LieAlgebra that's associated with the Lorentz group. The LieAlgebra will be seen as infinitesimal transformations moving to a frame of reference that's moving at a slightly different velocity. The invariants, furthermore, under the translations will later define the Poincare group and its associated LieAlgebra. Now, what does that mean? Well, it means that not only can we have rotations in x, y, and z, and Lorentz transformations between the t and the x, y, and z, which gives us 6 different parameters for our Lie group or our LieAlgebra, we can also translate in t, x, y, and z, giving us 4 more independent methods of transformation and giving us what is called the Poincare group by adding in these translations in space and time. We note that we can write our d tau squared as c squared dt squared minus dr squared, going back to our 3-dimensional type of notation, which is c squared t squared, pulling that term out, 1 minus, and here I've written dr squared over c squared dt squared. All I've done is factor this term out of this whole expression. This gives us c squared dt squared, and by taking dr squared over dt squared, we realize that is the vector velocity squared, or dotted with itself, divided by c squared. Now, if we take the ratio of this term to this term, we see that that is the square root of 1 minus v squared over c squared, or to take the reciprocals of both sides, c dt divided by d tau is equal to 1 over the square root of 1 minus v squared over c squared. It is incredibly important that one realize that this is the origin of the 1 over the square root of 1 minus v squared over c squared factor in all of the theory of relativity. It is the ratio of one clock to another clock that sits on the particle, as we'll soon see. In fact, one can see an indication of that right now, because if we can say, what is the meaning of d tau? And the answer is, if we have an object which does not change in its position, in other words, has a velocity of 0, then the right-hand side of this equation becomes 1, and d tau becomes c dt when the object is not moving. So we can see explicitly that d tau is c times the time interval that passes on a clock that's at rest with respect to the object in question. So d tau is a clock in the measured in units of meters that shows the passage of time on a system that sits on that particle itself, i.e., it is a clock that sits on the particle as it moves along. So d tau becomes an extremely important invariant. So how do we take derivatives with respect to time and relativity? Well, if we could take the derivative with respect to our own clock, but our own clock mixes up with our space in a very complicated way given by the Lorentz transformation as we go to a moving frame. In Newtonian mechanics, this worked extremely well because time was a scalar. Therefore, a vector divided by a scalar remains a vector. It is therefore imperative that we find a scalar that replaces our concept of time and allows us to take differential in order to form the concept of velocity. We can see what's going to happen next. We are going to have to use the proper time rather than to use the time in order to form a meaningful vector in relativity, and therefore the velocity for vector, the momentum for vector, and all other vectors and tensors that are associated with it. Otherwise, we will end up with something that is part of a vector on the top and another part of a vector in the denominator, and we will end up with a transformational mess that actually turns out to be a very, very complicated tensor with very unclear properties in terms of its physical meaning.